Hello everyone, welcome to the chemistry channel. So today we're going to be starting our 7th lecture on atomic structure by discussing the Pauli exclusion principle. However, in order to discuss the Pauli exclusion principle, we must also discuss the multi-electron atom. So with that, let's do a quick recap of the last video. So in one of our last videos, we talked a lot about the one-electron atom. And recall that in the one-electron atom, the energies of all subshells within a particular electron shell, so let's put a little more line here, are all equal. So in the one-electron atom, so a great example is the hydrogen atom, all the energy levels, all the energies of all the subshells within a particular electron shell are equal. And we saw this diagram in our last video. So we can clearly see here that all subshells in the second electron shell are degenerate, so let's circle this. All of these subshells are degenerate. And remember that degenerate means the same energy. So the 2p subshell is the same energy as the 2s. And the same applies to the third electron shell as well. All the subshells within the third electron shell are degenerate. So the 3s subshell is the same energy as the 3p subshell, and the 3p subshell is the same energy as the 3d subshell. So all subshells within a particular energy level have the same energy. So this is only true for one electron species, and this is due to the fact that in one electron species, there is no electron repulsion. So this is true due to the fact that there is no electron repulsion in a one electron species. So that's why all subshells within a particular energy level are equal to each other in energy. So this was all covered in the last video. If you have any questions about this, please post them in the comments. However, I go into it in a lot more depth in the last video. So please take a look at that if you are confused. So now let's look at what the multi-electron atom. So in the multi-electron atom, you have electron, so this means electron repulsion. So you have electron repulsion in multi-electron atoms. So the fact that all subshells within a particular energy level are degenerate does not apply to multi-electron atoms. So how would a multi-electron atom energy diagram look? So let's draw this. Let's use a different color here. So let's use purple. So we would start off with our 1s, of course, and since the first energy level does not have any other subshells except the 1s, we stop there. So now let's move to the 2s. So remember, for the hydrogen atom, we'd put the 2p subshell directly next to the 2s. However, in the multi-electron atom, we put them slightly above. So the 2p subshell has a slightly greater energy than the 2s subshell. So now let's move to the third electron shell. So in the third electron shell, you have the 3s. So actually, let's erase this. And that's because, remember, that as we increase in energy, as we increase our principal quantum number, the difference in energy decreases as well. So therefore, the difference between the 2s and the 3s subshell would be smaller than the difference between the 1s and the 2s. So let's put it a little bit shorter. So let's just say it's right here. So our 3s is right here. So the 3s, the third electron shell also has p orbitals, or a p subshell, and then we would use the same idea. The 3p subshells. The 3p subshell is slightly greater in energy than the 3s subshell. So let's write that here. And then what we do is we actually put the 4s subshell right here, and then the 3d subshell right, sort of right above that. So we're going to get more into why this looks as it does in a much later chapter when we start talking more about the periodic table and periodic properties. But for right now, you must know this general rule. And this general rule is that energy increases as our angular quantum number increases. So the energy of ns is less than np, and np is less than nd, and nd is less than nf. So as we go from ns to nf, the energy increases. So that is the general rule that you must know for right now. So if we look at this little energy diagram here, you'll see that there is some similarities with the hydrogen atom, or the one-electron energy diagram. And you'll notice that orbitals within the same subshell are still degenerate. So all the 2p orbitals are degenerate with each other. All the 3p orbitals are degenerate with each other. All the 3d orbitals are degenerate with each other. So orbitals within the same energy level, within the same, within the same subshell are degenerate. So orbitals within the same subshell are degenerate. So once again, all 3d orbitals are equal in energy to each other. All 3p orbitals are equal in energy to each other. All 2p orbitals are equal in energy to each other. So orbitals within the same subshell are degenerate. So now that we have this multi-electron atom, how do we go about filling up this orbital or energy diagram? Well, in order to fill up this multi-electron energy diagram, we have to have an understanding of the Pauli exclusion principle. So what is the Pauli exclusion principle? So we first, in order to understand what the Pauli exclusion principle is, we first have to understand that each orbital can carry 2 electrons. So each orbital can carry 2 electrons. So for example, the 1s orbital can carry 2 electrons. The 2s orbital can carry 2 electrons, and so forth. Each orbital can carry 2 electrons. However, how do the 2 electrons fill the same orbital? So how do these 2 electrons fill the same orbital? In order to answer this question, we have to bring up a certain topic of spin. So I'm sure you all sort of have a general understanding of what spin is. However, spinning does not only apply in our world, but it also applies in the quantum world. So subatomic particles can spin. So like balls spinning or something spinning in our world, subatomic particles can spin. So we can illustrate this by drawing a little circle, and we can call this circle our electron. And the electron has a certain axis that runs through it, so we'll just draw the axis like this. And the electron spins around this axis. So the electron spins around this axis. And this spinning around the axis is actually just called electron spin. So electron spin. So electron spin is the spinning of an electron around its axis. So these electrons are spinning around their axes. So you know that electrons have a charge to it. So the electron, let's actually use a different color here. So let's use something else. So let's use blue. So the electron has a negative charge. And this negative charge, so the negatively charged, so this means charged, electron is spinning. And whenever you spin or move a charge, the spinning or moving charge forms a magnetic field. So whenever a charge, so this means charge, spins or moves, a magnetic field can be generated. So whenever you have a charge spinning or moving, a magnetic field can be generated. So when an electron spins, it forms a particular magnetic field with a particular direction. So note that electrons can spin in a positive or negative direction. So electrons can spin in a positive or a negative direction. And each direction produces a different, so this means different, magnetic field. So each direction that the electron spins produces a different magnetic field. And these magnetic fields are opposite in sign. So these magnetic fields are opposite in sign. And physicists and chemists have looked into this, and these magnetic fields and these spins are actually quantized. So the electron spin has been found to be quantized. And this quantization of electron spin has actually been given a quantum number. And this quantum number is ms. So ms is the quantum number for electron spin. And ms can have two values. Can have two different values. And these two different values, so these two different values are plus or minus 1/2. So ms can either be equal to plus or minus 1/2. So what do these plus or minus mean? Well, recall that the plus and minus indicate two different spin directions. So we symbolize plus spins as an upwards half arrow, and we symbolize minus spins as a downwards pointing half arrow. So this upwards arrow corresponds to the plus 1/2 spin, and this downwards pointing arrow corresponds to the minus 1/2 spin. So these spins are the spins each have a value of 1/2, but only differ in the direction. So each of these spins has the same value associated with it, but they only differ in their direction of orientation. Therefore, each spin produces a magnetic field with an opposing direction to its opposite spin. So the plus 1/2 spin produces a magnetic field that is opposite in direction to the minus 1/2 spin. So now that we know that electrons can occupy different spin states, we know that we can now understand the Pauli exclusion principle. So the Pauli exclusion principle states that no two electrons with the same N, L, and ML value can have the same MS value. So no two electrons with the same NL, ML value can have the same MS value. So what does that mean? So let's just do a 2p subshell. So let's look at the 2p subshell. So remember that the 2p subshell has a principal quantum number equal to 2, an L value equal to 1, and the ML values can range from negative L all the way to L. Therefore, we range from -1 to 0 to 1. So we'll label each of these orbitals -1, 0, 1. Let's actually say we have 4 electrons in the 2p subshell. So let's just draw it like this, and we'll learn more about this in the next video, so don't be too concerned about why I did this for right now. So how would I orient the 4th electron in this -1 orbital? So let's just focus in on this -1 orbital now. So -1, and we have this electron in this particular spin state. So according to the Pauli exclusion principle, I can only write the second electron like this. So it must only have a MS value opposite to that of the other electron occupying the orbital. So let's write it down here. In order for 2 electrons to occupy the same orbital, they must have opposite magnetic spin numbers. So they must have opposite magnetic spin numbers. So you cannot write an orbital with 2 electrons in it like this, or like this. So these two are wrong. The only way you can write it is if one has a plus 1/2 magnetic spin quantum number and the other one has a minus 1/2 magnetic spin quantum number. So that is the Pauli exclusion principle, and this will prove to be very important in the next lecture. So in the next lecture, we're actually going to be wrapping up atomic structure by talking about the electronic configurations of different atoms. So we're going to be concluding atomic structure with that discussion. So I hope to see you all in the next video. I hope this video helped clarify something for you. If you have any questions, please put them in the comments section, and I hope to see every one of you next time. Good luck, guys, and see you around.